Welcome to our discussion of velocity and acceleration. By the end of the day, I hope that you can be able to understand that velocity and acceleration, while they're related to each other, are very distinct and different ideas. To do this, we're going to be talking about the three ways that you can accelerate. I'm going to show you how to calculate acceleration, what things you need in order to calculate acceleration, and to drive home the point, we're going to really try to clearly distinguish between what velocity is and what acceleration is. All right, so let's get started. So there are three different ways to accelerate. Now, as we think about these three ways, we're going to categorize motion into 5 different categories. So all objects at all time in the history of the universe are in one of these 5 categories. The first one is simple. It's staying still. So an object can just sit there, right? We know that. And objects can move, and they can move at a constant speed. So you can drive your car at 55 miles an hour on the interstate. The next thing they can do, of course, to get to that 55 miles an hour, you have to be able to speed up. So that's another category of motion. And of course, if you can speed up, then surely you can slow down. And that's the fourth category. Our fifth one is that you can turn. So you can use that steering wheel to turn. Now, as we look at these these 5 categories, there are really 2 categories inside. These first 2 can be grouped together. And these first 2 are things that just happen. They happen on their own. We don't have to mess with them too much. So if we want something to stay still, we just leave it alone and it stays still if it's already still, right? And if something's moving at a constant speed, we just leave it alone and it just keeps moving. Now this one might be a little harder to see because friction does tend to slow things down on Earth. And in fact, anywhere, not just on Earth, but friction slows things down. If we look at a low friction environment, say you're playing air hockey, and you slide the puck along the table, it does a really nice job at maintaining a nice constant speed as it glides over the table. There's a little bit of friction, so over time it will slow down. Now these 3 down here, these are very different. These have to have a cause. So they have to be caused. They don't just happen on their own. So for example, if you throw a baseball to a friend of yours and halfway across in the air, it suddenly slows down, stops, turns around, speeds up, and comes back at you, you'd think, well, that was really strange. And that's because these 3 things require a cause. Now, when the baseball hits your friend's hand and your friend slows the ball down and speeds it back up and throws it back to you, all that makes sense because there's an obvious cause for it. So these have to have a cause associated with them. And these are the ones that we call acceleration. These are the 3 ways you can accelerate. You can speed up, slow down, or turn. And those are the only 3 ways you can accelerate. Now, these other 2 up here, the stay still thing and move at a constant speed, these are not accelerating. So all objects are either accelerating or they're not accelerating. There is no in between, right? That's our 5 types of motion. So our 3 ways to accelerate, just to recap, speed up, slow down, turn. That's going to become important over the next few months. Now let's check our understanding. So here we have a comprehension check, and I've listed 7 types of motion, or 7 descriptions of motion here. For each one, you're going to indicate an A for accelerating or an NA for not accelerating. So go ahead and pause the video right now. Give yourself a chance to read through them and record kind of what you think the answers are. When you're ready to hear the responses and check your work, go ahead and hit play again. All right, let's get started. So right after hearing the starter's pistol, we're assuming that James is going to speed up since he was stopped, so that's accelerating. And you're sitting watching YouTube videos, well, you're not speeding up, slowing down, or turning, so that would be a not accelerating. Now, you might say, but wait a second, I'm sitting on the earth, and the earth is spinning, and I'm spinning with the earth, so I'm turning around the earth, so I am accelerating, and you would be absolutely right. So if you put accelerating on that because you're sitting on the earth and accelerating around the earth, then yay for you, you're right. Megan walking at a constant speed of 1.5 meters per second around the track. It's the around the track that gets us. So we can see that she's not speeding up or slowing down, but she is turning as she goes around the track. In fact, tracks are typically shaped straight stretches and then curves. So during this part of the walk, she's accelerating around the curve. The straight part, she's not accelerating, and then accelerating around this part of the curve as well. So on this one, you could say accelerating and not accelerating. I'm going to put accelerating down because she's going around. Now, David walking down a straight hall at constant speed, well, that's not speeding up, slowing down, or turning, so that's not accelerating. Now, Sarah running into a glass door that she thought was open, she's going to go from moving to stopped really quickly and probably using mostly her nose to do that with, so she will definitely be accelerating because she'll be slowing down. A rock dropped from a second floor window, right? So this one, when you let go of the rock speeds up and it accelerates. As baseball is being released by a pitcher. Now, at first you might say, well, oh gosh, that won't be accelerating because nothing's pushing on it because the pitcher's let go of the ball. But then you have to remember, oh, but gravity is pulling down the ball, right? So we have a ball here, we have gravity pulling down on it, and we have wind resistance pushing back on it. So we end up having this, so it's going to actually slow down and fall, so it's going to be accelerating. And remember, it's going to take this trajectory, right? So it's going to go, it's going to curve down like that, so that's a turn in there. And it'll be slowing down some, so it's accelerating. All right, awesome job. Check your work. Hopefully on that you should have gotten a 6 or even a 5 out of 7. A 7 out of 7 is even better. Now that we know the 3 ways that we can accelerate by speeding up, slowing down, or turning, we're going to learn how to calculate acceleration and what things go into an acceleration calculation. So a common way to quote accelerations for cars is to say you can go from 0 to 60 in so much time. So for example, the Tesla Roadster, which is an all-electric vehicle, can accelerate from 0 to 60 miles an hour in just 3.7 seconds. Right, so this is a good way to illustrate what goes into acceleration. There's this thing here, which is a change in velocity, so it's a speed up or a slow down, and the time that takes to happen. Now our acceleration equation is going to be acceleration is equal to the change in velocity, so how much you sped up or slowed down by, divided by the change in time, how much time it took you to do that. Now, if we look at this number and we say, okay, what will happen if we change this number? What if instead of going from 0 to 60, we went from 0 to 90 in that same 3.7 seconds? Of course, that would require a greater acceleration, so your acceleration number should get bigger because you have to speed up more. Just like if we were to decrease this number, if we were going only from 0 to 30 miles an hour in 3.7 seconds, that would be a smaller acceleration. It would be easier to make that happen because you're speeding up slower. And the other part of acceleration is the time component. So we can affect our acceleration by changing the amount of time it takes. If, for example, to go from 0 to 60, instead of taking 3.7 seconds, we did it in just 2 seconds, that would be a much faster acceleration because we have to speed up that 60 miles an hour in less time. And likewise for more time. If this took 10 seconds to go from 0 to 60, that would be a much slower acceleration. You have more time to build up that speed. So let's do the calculation real quick. So our change in velocity here, we're going to write it down. From 0 to 60 is 60 minus 0, so it's 60 miles per hour. And our change in time here is 3.7 seconds. So we can plug these into our equation. We're already solved for acceleration. We have 60 miles per hour divided by 3.7 seconds. We plug that into our calculator and we get 16.2 as the answer. Now to figure out the units, we have to see if anything cancels. So hours on bottom, seconds on bottom, these two don't cancel. So we have miles per hour per second. We have these strange units of miles per hour per second. Now as you think about what these units mean, so acceleration is how fast we're speeding up. This means that we speed up every second. We speed up by 16.2 miles per hour every second. So after 1 second, we're going 16.2 miles per hour. After 2 seconds, we'd be going twice as fast, which is 32.4 miles per hour. And then 48.4 6 miles per hour in 3 seconds. So every second you speed up that much. And if you speed up this much every second, in 3.7 seconds, you'll be at 60 miles per hour. So units of acceleration are distance per time per time. It's a speed, how much your velocity is changing per second. So remember, that's acceleration. And the fact that this is a positive number means that we're speeding up, not slowing down. So the two things you need for acceleration is how much your speed changed by your change in velocity and how long it took the change in time. Pretty quiet?
Yeah. Was it cold on the way up here? Wow, that can turn easy. That thing goes fast in a short period.